there exists a delta that depends only on epsilon this time, greater than 0, such that f of such that the magnitude of x2 minus x1 being less than delta will imply that the magnitude of f of x2 minus f of x1 remains less than this epsilon, where x1 and x2 are both in this subset S. So note the real difference here when I put in the word uniformly is that delta doesn't depend on x1 or x2. Only depends on epsilon in this case. And then I can throw in that adjective uniformly. So basically, in this case, we're just saying the derivative exists. So essentially, you're saying it's differentiable. So definition, a function f that maps some subset of the real numbers into the real numbers is piecewise continuous if it exists in S, and it is not continuous only at discrete points. So I'm going to have a function that looks like this. So at those discrete points, it's not continuous. So if f of x looked like this, then you would say f of x is continuous on set negative infinity to 0, not including 0, and 0 including 0 to positive infinity. It is uniformly continuous on negative infinity to negative 1, not including negative 1, not including negative 1 to 0, not including 0, including 0 to 1, not including 1, including 1 to infinity. And it's piecewise continuous on negative infinity to infinity. I can just say it's piecewise continuous. I don't really have to write negative infinity to infinity, because if I write piecewise continuous, that implies piecewise continuous everywhere. So you can see that nonlinear systems are more complicated than linear systems. In linear systems, you would just say something was continuous or not continuous. In fact, a linear system would be continuous. So you get these kind of things in nonlinear systems where something, has a certain property in a certain domain, but a different property if you're talking about a different domain. So you always have to be like, you can't just say the adjective for what describes your system. You have to say where that adjective is going to apply as well. So you often end up having to include what domain you're talking about when you qualify what kind of system you're talking about. So let's do some set definitions now. If I was describing something as being a sphere or a ball around x naught, so x naught is in Rn, which just means it can be an n-dimensional vector of real numbers, is the set Vr. Described by x such that x, the norm of x minus x naught is less than r for some r. So note, normally when you write a norm, you're not necessarily talking about the 2 norm. You could be talking about any general norm. That's the case here, that you could actually use any norm you wanted to. So r is literally the radius of a circle if we use the 2 norm definition in this norm. If you use the 2 norm here, and you put an equals sign here, you're talking about the equation of the circle, right? But this definition technically holds no matter what norm you use there. But we'll stick with the 2 norm in this course. We'll just always assume we're talking about the 2 norm. So a lot of these definitions and theorems will apply no matter which norm you use. But for our purposes, we're going to be fine just assuming we always are working with the 2 norm. So now, from now on, we will mean the 2 norm when we write the norm of x by assumption. So if you're not sure what the 2 norm is, that's when you have to get studying for this quiz. So that's the kind of information that's in the back of the textbook and all the appendices, just to refresh your memory what we mean by this kind of mathematical notation. So that's the kind of stuff I want you to study for the quiz. So mostly I'm getting you to write this quiz just so you know what I'm writing on the board in the lectures. Right? That's about it. That's really the purpose of the quiz. So definition. An open set does not include its boundary. So an example of an open set is 0 and 1, where 0 and 1 are not included. So that would be x and r such that x is greater than 0 and less than 1. Another way of writing that, those two forms of denoting the set are exactly equivalent. And B2 is another example of an open set where we would have this being less than 2 and not less than or equal to 2. So you notice we put right in the definition of what we meant by sphere or ball. We didn't actually include its boundary. So by definition, a sphere or ball doesn't include its boundary. Okay. So a closed set contains its boundary. So 0, 1 with square brackets would indicate x in the real numbers such that x is greater than or equal to 0 and less than or equal to 1. And a bounded set is contained within a finite sphere. So S is some subset of VR. If I was to draw that, I have some set S here, and that's contained within some nice ball VR. Okay. Compact set is both closed and bounded. So a function f that maps some subset of Rn to Rm. So where D is an open subset of Rn, it's a vector, an n vector of real numbers. So I could just write like that, D is a subset of Rn, is continuously differentiable in D if the magnitude of diF dy minus diF dx is less than epsilon for all x and y in this subset D. the magnitude of x minus y is less than delta with some constant delta greater than 0. So the theorem kind of makes this practical for evaluating is that f is continuously differentiable in D if and only if partial derivatives exist and are continuous in D. So it's pretty easy to check if something is continuously differentiable. Just take all the partial derivatives and take a look at them. So you don't actually, so the nice thing about the theorem is it means you don't actually have to play this game with the epsilon and the delta anymore. Although that's the formal definition. If you actually want to check to see if something is continuously differentiable, then you just do this rather easy check of taking the partial derivatives. So something that pops up a lot when he's analyzing linear systems is Lipschitz continuity. So Lipschitz continuity is kind of like a stronger version of continuity. It's stricter than the regular definition of continuity. So if it's Lipschitz continuous, then it's definitely continuous. But if it's continuous, it might not be Lipschitz continuous. A function f that maps D into Rm, where D is a subset of Rn, is locally Lipschitz on D if every point x naught of D has a neighborhood D naught is a subset of D over which the norm of f of x minus f of x naught is less than or equal to L times the norm of x minus x naught for all x in D naught of x naught, where L is a constant. So basically, I mean, divide this by this. I mean, we're basically talking about the derivative here, the magnitude of the derivative. So, I mean, L is a constant, so you're basically saying you have a finite derivative. So the derivative can't be infinity. So that's actually pretty strict. So mostly when you talk about systems being Lipschitz, usually you're talking about locally Lipschitz, because often functions go off to infinity as you go to negative infinity or infinity, right? So usually you're talking about something that's locally Lipschitz, but I mean, if you're talking about, there's kind of like a very limited number of functions that would be globally Lipschitz, but something like a sinusoid, like sine x, that derivative is very well defined. It's finite. It's finite everywhere. So that would be something that would be like globally Lipschitz. So the function f is Lipschitz, meaning globally Lipschitz, if magnitude of f of x2 minus f of x1 is less or equal to some constant L times the magnitude of x2 minus x1 for all x1 and x2 in D. So for example, f of x equals x squared is locally Lipschitz. F of x equals sine x is Lipschitz, and I'll just put in the brackets here, globally Lipschitz, although you wouldn't normally say that. It's kind of understood. F of x equals 1 over x is not locally Lipschitz if D includes x equals 0. Because obviously in x equals 0 you get infinite slope there. Okay, so basically having this requirement that you have a finite derivative is actually a stronger requirement than continuity. And often when we do this nonlinear analysis or nonlinear control systems, often we do have this restriction where something has to be locally Lipschitz in order to get these kind of guarantees that we want out of the system. So it is a kind of a difficulty sometimes to kind of verify that something's locally Lipschitz, but often it's necessary to get these controls to work. So that got us through these definitions. So now we can kind of get back on track and talk about the interesting parts, nonlinear systems again. So when we talk about nonlinear systems, basically nonlinear systems can be divided into two classifications. One would be autonomous systems, and one would be non-autonomous systems. So a non-autonomous system has t appear explicitly. So, I mean, obviously these things are functions of t, because we have x dot here, right? So that's obviously dx dt. So obviously we're just talking about x being a function of t. But if you write something like the pendulum, we didn't actually see the variable t anywhere inside the pendulum equations, even though all the variables actually depend on t. In a non-autonomous system, you actually see the variable t pop up explicitly. So something depends explicitly on time. Now, why would this occur? So like in a pendulum system, like, yeah, maybe friction could depend on time, but that's probably really slow time dependence. So, friction might change from day to day as humidity changes and things like that, temperature changes. Friction could definitely change, but that's such a slow kind of change. You normally wouldn't think about including that in a control system or think about modeling it in the pendulum equations. It would be a very strange thing to do just because it's such a slow change. What else could change in the pendulum? Well, I guess, maybe your mass is, evaporating or something, but that would be also a very strange situation. So it's hard to think of a physical reason for time to appear in something like the pendulum equation. But when I talk about designing nonlinear control systems for pendulum, I'd almost certainly think of it as a non-autonomous system. So where does the time dependence come in the pendulum system? Where does t pop in from? The speed? In what way?
Laws of friction dependent speed.
Yeah, so I have velocity, so I have like x dot. So like I said, this x dot here, it is time dependent in the sense that definitely depends on the variable time.
Oh, right, yeah.
But I don't actually see t there. I don't actually see the variable t.
Maybe disturbance?
The disturbance, so if there was a disturbance in the pendulum system, it could be a time varying disturbance. That's possible. Well, even a pendulum that had no disturbances to speak of, no significant disturbances, when I do the control systems problem, I'll probably see t. Why?
Maybe relative to your start time?
Relative to the start time? Well, that would be t naught. So t naught would be like a constant. But even t naught wouldn't necessarily appear in the pendulum equations. It shouldn't anyway. Like your initial condition, x naught might, but probably not t naught, because t naught is probably 0 anyway. You can always assume you start at time 0. So think about previously in this lecture the way I was talking about linear and nonlinear controls and when I would use a linear control for a pendulum and when I would use a nonlinear control.
Trajectory, tracking.
Yeah, so like I said, so the pendulum's sticking straight out and I want it to stay straight out and just stay there. That would be like an autonomous system. But in that case, I'm probably just going to design a linear control. So I probably wouldn't really get into nonlinear control theory if I was doing that particular problem. But if I wanted to follow a trajectory, then that's probably when I want to get into designing a nonlinear control. And in that case, my trajectories could be cos t, if I want to do a periodic trajectory, sine t, but the desired trajectory is going to depend on time. And the equations for the desired trajectory will end up inside my nonlinear equations when I design my control system. Yeah?
So that means that you've spec so that t is specific for you.
Sorry?
So that t is relative for you then, right? Like that's your control input's time.
It's not a control input, it's a desired trajectory. So the control input will be the torque in a pendulum. But the controller could also have a desired trajectory input into it as well as the actual measured positions and velocities. So if I was trying to follow sine t as my desired trajectory, I would definitely end up with a sine t somewhere in my equations of motion for the system now. And all of a sudden I would have a non-autonomous system. So other nonlinear control books are kind of, because what we're going to do is we're going to look at Lyapunov theory and Lyapunov theorems for designing nonlinear systems. And so basically every other textbook but this one kind of gently introduces you to nonlinear systems by giving you a bunch of Lyapunov theorems for autonomous systems. And then once you're kind of comfortable with that, it brings you into the world of non-autonomous systems. And it introduces T, and then all the Lyapunov theorems kind of change slightly. But then you find out that, oh, when you realize how you actually apply these things, all the Lyapunov theorems you learned about x dot equals f of x are actually useless, because you're never going to design a nonlinear control for an autonomous system. So this textbook by Zach, I kind of like it, because it skips over the theory of autonomous systems almost altogether. It just kind of briefly mentions it. And Zach kind of directly goes to these non-autonomous systems, because that's what you're actually going to use. So why bother learning the theorems for the useless autonomous system thing? Because basically, if you see a system like that, probably you're going to design a linear control, even if it's a nonlinear system. It's when you get into systems that look like this that usually you get interested in nonlinear controls. So we're probably going to do the same. We're going to probably follow the same track as Zach and kind of skip the gentle introduction to Lyapunov theorems using autonomous systems and go directly to these nonlinear system things, because in a sense it's a bit of a waste of time to learn all the theorems about autonomous systems. So that's why this textbook is quite a bit different from other nonlinear control textbooks. But that may save us some lecture time as well, if I don't have to write all these theorems twice. If I can just do the non-autonomous systems. So, oops, I went a bit over time, but I really want to stop at 4:45. Normally I would. So yeah, we'll see you next Monday, and think about your projects a little bit, but there's not too much you can. Nobody said they were going to do something else in the flexible joint robot, so you don't have to worry about it too much. I'll introduce you to the things you need to know about your project in the next couple of lectures. And remember, 2 weeks from now is the quiz, but if you start studying for it now, then you'll understand what's going on in the lectures much better, because I'll be using symbols and terms in the lectures that really you should probably know from studying for the quiz. So think about starting to study from the quiz right away, just so you understand the next lecture much better. Okay, so we'll see you next week.